Welcome everybody. So before we start, I just wanted to throw in a couple of questions to see how much we retained from last time. The first question should be fairly easy. How do we decide the k in k-means? What's one possible way? So given a data set, you have been asked to cluster it, and for whatever reasons you have decided to stick to k-means. Nobody is going to give you the value of k a priori. They might not, right? They might or they might not, right? There might be some natural values of k. For instance, in the MNIST data set that we saw, there was a natural value of k because there are only 10 digits. So their k is clearly 10, right? That's the right value, possibly the right value. But suppose it's a data set you don't know anything about. What would be one possible way you go about choosing the value of k? Huh? Sorry, you? So what is the, so you plot a graph. So what is the graph? So we talked about plotting a graph with the number of clusters on this side and with the objective function cost on this side, right? And hopefully the graph goes something like this. I mean it is decreasing, of course, right? And we saw the proof of that. But maybe there's some nice point beyond which it sort of falls quite as much, and at some point it's going to become more and more flat, right? The cost of adding more and more clusters I mean the benefit of adding more and more clusters is going to decrease. So you have to decide based on this that what is the right value for me, that I can bear with, I can kind of deal with this objective function cost or this kind of error in my clustering, and therefore this is the k that I'm happy with. Okay, fair enough. That's fine. Let's stick to that. Now let's change something else. So we defined the Lloyd's algorithm or the k-means mostly for the L2 norm, right? Mostly for the Euclidean norm. So suppose somebody came and I mean you have implemented it, suppose, and somebody suddenly comes to you and says, oh no, I don't want the L2 norm, right? I want the L1 norm. There are many reasons. I mean L2 norm is more sensitive to outliers. If there's one particular coordinate that has a large value, L2 norm is very sensitive to that, and so on. So somebody wants the L1 norm. How much would you have to change in your algorithm? What would you have to change in your implementation of the Lloyd's algorithm? The cost function, okay. But the cost function changes, that's fine, but the cost function is not really part of the algorithm. What would you have to change in the algorithm? Instead of mean, you have to take something else. What is that? You have to take median. So instead of when we define the center, when we define the, let me call this, when we define the center of the ith center of I, we now define it as the median of x belongs to Ci x. So what does this really mean? I'm sorry, I'm just drilling down. What does this really mean? This x is a vector. Remember, this x is a vector. So what does taking a median of a d-dimensional vector really mean? Sorry? Center. But how do you find the center? What do you mean the center?
Center of ordered values.
What do you mean there? I mean, how do you calculate it? So the mean was easy, right? So we defined that we said that I mean if you have to take the mean, you just average the vectors. We're very familiar with that. This is also a fairly easy, easy thing to do. It's just that you have to get your head around it, right?
For each coordinate, we can take the median.
Absolutely. For each coordinate, so what do you do when you take the mean? You take the mean of every coordinate, right? You go over all the points for the ith coordinate. You take the mean of the ith coordinate. Here, you have to go over each coordinate, take the median of the ith coordinate. As simple as that. That's all you have to change in the algorithm, right? So the point assignment remains the same. Every point gets assigned to the closest center, except that now the assignment, everything happens using this norm, using this new norm, which is this L1 norm. Thank you. Good job. Okay. So now let's start. So today we're going to do dimension reduction. And so I took a lot of help from the slides from Piyush, who actually will be coming here to teach you something, and David Sontag. So thanks to them. So what is dimension reduction, right? So dimension reduction is, so there are many different interpretations, right? Usually it's an unsupervised technique, which means that usually you're just looking at the structure of the data, not really at the labels. However, thank you. That is not given, right? I mean, there are aspects of dimension reduction in which you consider the class structure of the data, the label structure of the data. We won't touch upon them in this class, but maybe later in your course you will face that, right? So, what is the motivation? The very broad motivation is that we want to discover low dimensional structure in the data, right? And this, while sort of I'm stating it in one line, this could be a surprisingly complex thing to do. So take this very simple example in which, so this is probably the simplest example. We have points in 2 dimensions, right? So we have the blue points, we have the red points. We have the blue points here. So every point has the coordinate x1i and x2i. That's the ith point. Okay. So what are we doing here? What we are saying here, okay, that I'm not even interested in storing 2 dimensions from every point. Can I fit a line through these points, right? So of course, if the points are collinear, then the line is easy to fit, right? But what do you do when the points are not collinear? You have to, in some sense, get the best possible line to fit through that. So what is this notion of best, right? And these are the things. So just like in clustering, we define the distance function, objective function, and so on. We have to do similar things here. That we have to define a notion of best. We have to define what are the possible low dimensional structures we are fitting, right? We'll see that low dimensional structure can be a subspace, it can be a non-negative cone, and things like this. So we'll go to more and more complicated things. So here we're just interested in fitting a line, right? And then we ask the question, okay, what are the distances of every point? What is the representation of every point according to this line? What would be natural representations of every point on this line? So is my question clear? That you want to approximate the blue points, right, by a set of representatives that all lie on this line. So for every point you have to find out, okay, what is the best representative of this point on this line? What would you do? Perpendicular distance, that's easy to say. Why are we doing perpendicular distance? That's the shortest. So that's the shortest in what norm? That's the closest in what norm? Okay. So there's a lot of assumptions we took in here, right? We said that we are going to take the projection of a point x onto the line. Okay. So what is this projection, right? We kind of define that, okay, so choose a point on the line, we are calling it xi tilde here, such that some distance between xi and xi tilde is minimum, and xi tilde lies on the line. Okay. So now it's very intuitive to us that if this distance happens to be Euclidean distance, which is basically the shortest distance on the line, right? Then the best thing you can do is just draw an orthogonal, basically just drop the point on the line, which is what we are doing, right? We are dropping the point on the line, and then this is of course the shortest distance from the line to the point. And so that's the corresponding representation. So what would I do, for instance, if this distance was L1? Any idea? What would I do if the distance was L1? It's not actually easy to see. You have to, so L1 distance is measured in terms of the amount you have to go here plus the amount you have to go here. So in some sense, you have to solve a little more complicated objective function, optimization problem, right? And it might not be as easily visualizable as here. So let's come to this next example, number 2, right? So here, for instance, you have these dots that you see, right? These are all data points. So let's say that the data points are all in R3, Okay, and when you first get these data points, you look at them, stare at them, and then you say that okay, they are all in 3 dimensions. There's nothing much we can do, right? However, if you happen to come upon this visualization, right, you might be able to say that look, while they are mostly in 3 dimensions, right, it's possible to kind of fit a sort of 2-dimensional surface through it, right? Although it's not a flat 2-dimensional surface, right, it's what is known as locally flat, in the sense that in the topological sense, this really looks like a plane, right? So just like there's a little difference between the surface of a sphere and the surface of a plane, there is little difference between this plane rolled in here and this plane as flattened out, right? So then the question becomes that can I find a mapping from R3 to R2, right, that takes this 3-dimensional representation of the points and rolls it and maps it into the surface of the plane, right? So what do I want to preserve? There must be something I need to preserve, right? Because otherwise I could have just taken any mapping from R3 to R2. What do you think I need to preserve here? Variance of the data, that's true. But in a more concrete sense, I mean in a more ground to earth sense, I kind of want to preserve. We'll take projection of the data, but the projection needs to preserve something. So I kind of want to preserve the distance structure of the data, right? For instance, if 2 points are here and here, they're pretty close by according to the surface of the sphere. I want them to be their projections to be fairly close by, right? But it might happen, right? It might happen that 2 points that let's take one more extreme example. Let's take 1 point here and 1 point here. So these two are fairly close according to this, right? But if I consider the underlying structure of the data, right, and if I'm moving only along this surface, right, then they're not very close, right? And so these 2 points, let me call that C and D, right? So these two, one of them lies here and one of them is lying here and one of them is lying here, C and D, they will be pretty far off, okay? But in some sense, what will be preserved is the local distance structure. Okay? That for every point, if you look at all the points in its neighborhood, if you take a small ball and look at all the points in its neighborhood, that will be that distance, all those pairwise distances will be preserved here. Okay? So this is a notion of local dimensionality reduction. Right? So, and then there are many such variants. But let's come up on what is it useful for? What do you think dimension reduction is useful for? And obviously this is a blank slide because the answers are going to come from you guys. What do you think it is useful for?
Sometimes you need to send a single vector of data to the plus any other thing. You can't send like images. So you convert it to.
So you're doing okay. So the answer there is that you don't want to be sending a lot of data to my classifying algorithm, right? So in some sense, what you're saying that you're doing a compression of the data. Is that accurate?
Yeah, I mean like images are like 2-dimensional, but the algorithm can't directly process that. It needs a 1D conversion.
Well, I mean, there are many ways of going from a 2D to 1D, right? You could always linearize it. So that's not really a problem. You don't really need to do anything more complicated for it. But you could be saying that look, I mean, there is all these data, maybe very high dimensional data, and maybe it's pretty large. And I don't want to be storing a very high dimensional representation of it, right? If I do for instance here, right? If you at least think naively that this is for every point, you're storing 3 coordinates. Here for every point, you are storing only 2 coordinates. So of course there's a 30% reduction. Potentially there's a 30% reduction. This gets more complicated if the data is sparse and so, but potentially there's a 30% reduction here. Here there's a 50% reduction. From 2 coordinates every point, you're storing 1 coordinate every point, right? So potentially there's a compression effect. What else?
Redundancy. Redundancy. Things which are getting repeated again and again.
Redundancy. That's a good point. That suppose there are multiple features in your data that are really more or less the same, right? So in theory, in sort of more concrete terms, we would say that if two different features are very strongly correlated with each other, right, dimension reduction is likely to remove one of them. What else?
We can't visualize the higher dimensional space. So by using dimensionality reduction, we can reduce it to 2 or 3 dimensions.
Okay. Visualization. Visualization, excellent. What else?
Reduce the cost to supervised learning techniques.
Reduce the cost. What kind of cost?
If dimensions are more, then it will take more time to process.
Reducing time complexity of downstream processing. Is that an accurate representation? That I mean, you could look at this as some form of pre-processing of the data, so that whatever you do with the data later on, if the cost of that depends on the dimension, then you have reduced the dimension, right? Anything else? I'm kind of squeezing as much as I can out of this. Removing unwanted features, we already covered that. Removing redundancy, I think it could fall in that. Anything else?
There are certain things that won't work in high dimension. For example, it is not that Euclidean distance doesn't work well for high dimension.
What doesn't work in high dimensions? Distance.
Finding Euclidean distance.
Finding Euclidean distance.
Dimensions are high.
So that statement I know. So the question was that the point that is being made is that there are certain things that do not work well in high dimensions, and I think what is being meant by this is known as the curse of dimensionality, right? This is a standard term, that dimensionality, right? This is a standard term that you will see. What it really means is that, in very broad terms, and we'll see this, that if you will come to this. We'll come to this. So if you have higher and higher dimensions, right, then in some sense a lot of the complexity can depend exponentially on the dimension, and we'll see why. And this will help us with that. It's also an implicit regularization, although you guys haven't really defined, don't really know in a formal sense what regularization is. We talked about it sort of intuitively yesterday, and similar, and it's like, so I'll just define what it is. Again, of downstream, let's say classification. Right? It's like saying that look, so imagine this kind of a pipeline in which you are doing dimension reduction of your data, and then maybe you're learning some classifier on the reduced set of features, right? So what have you done? Instead of learning a classifier that works in d dimensions, now you're learning a classifier that works in only k dimensions. So in some sense, what you have done is that you have reduced the complexity of the classifier, right? And reducing the complexity of any classification technique, of any kind of model, is known as regularization, right? You will see that there are very good reasons to try to do this. And dimension reduction, you could also consider this as sort of implicitly trying to sort of achieve this. This is excellent. See this. So one thing that we kind of missed is we kind of covered this, is that what we'll see is that sometimes what will happen, a lot of times what will happen is that we'll have very sparse data that lies in very, very large dimensions, right? So imagine that you have document, right? And these documents, we represented them yesterday as a vector over whatever dictionary that we have, which is potentially very large. But each of the documents are fairly small, right? Imagine a document is a tweet, 140 characters, right? And like 10 words or 15 words. Imagine a document is even a New York Times article. How many words? 1,000 words? Not much more than that, right? Whereas the dimension of this, we said, was easily 100K. If you are considering all the bigrams and so on. So documents are very, 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 very sparse vectors. Most of the entries are 0, right? And sparse vectors doing anything with the sparse vectors, brings in a lot of noise, right? Because even if you're comparing two sparse vectors, if you're, that's sort of, the results are pretty noisy. So, I'm talking in a very hand-wavy sense. What this dimension reduction is trying to do is essentially convert this into a much lower dimension by trying to find out that, okay, that this feature and this feature maybe are more or less correlated, right? Again, this is very intuitive. This is not exactly what is happening, but that's kind of like the structure. That maybe this feature, this feature, this feature, this feature is a linear combination of this feature and this feature, right? In that case, we can kind of combine these, right? So that's the kind of intuition that you should keep in mind. That's what dimension reduction is happening, right? And this, it's possible to sort of frame this in pretty complicated ways, and this is known as representation learning, right? Overall, this and we're not going to go into the details of that, but just to sort of make you familiar with the terms, and we have covered all these other aspects of dimension reduction. Okay, so here is where so we started talking about this curse of dimensionality. So what does it really mean? And let's see a very concrete example. Okay? So imagine that we start with this line, with a single line, right? And we're trying to find, okay, that suppose we want to partition this line into unit interval sizes. Okay, and if the line is of length L, okay, how many intervals do I need to fill it up? L intervals. Okay, but now suppose we have a two-dimensional space, right? Again, we have this x1 and x2, and both x1 and x2 individually can go from 0 to L. And then the area corresponding, so just like in 1D we had this unit intervals, the corresponding area here would be a unit square. So how many unit squares do I need to fill up this area? L square. I'm asking very trivial questions. When we go in 3 dimensions, L cube, we need L cube unit cubes to fill up this area. How many do I need in d dimensions? L to the power d. Right? Why am I asking this? Right? So imagine these are features. This x1, x2, x3 are features. Okay, and and imagine they take discrete values. Right? They take values 0, 1, 2, 3, 4, etc. up to some max of L. Okay, so then what would happen is that if you have a d-dimensional feature vector, right, the total number of possible values that this feature vector can take is what? So you have a d-dimensional feature vector. What is the, so and each value ranges between 0 to L. What is the possible set of values of this feature vector? The same question that you guys answered. L to the power d, right? So in most typical cases what would happen is that supposing, assume that L equal to 2. Let's say that the features are binary. So what is happening if the features are binary? The number of feature vectors is already 2 to the d. And in the d that we are talking about, let's say d equal to 100k, this is like 2 to the 100k. Right? What this means is that if you have a reasonable data size, if you have realistic data size, that will be always much less than this number. Right? What does that mean? Well, what that means is that most of the feature combinations in any realistic data size, you won't even see most of the feature combinations happening. You won't even see this feature and this feature coming together. And that's not because these two features are not correlated. It's just that your sample size is much smaller compared to the set of possible universe that you have, right? So is this concept clear? Right? That even if two features have like a 30% chance of appearing together in the same document, right? You would need about 2 to the d divided by 30%, 30% sort of sample in order to see these two features appear together, right? And to do that, I mean, but the number of samples that you have is much less, much less. Sorry, which is so this number, okay. Maybe I sort of missed out a little, but okay. But then basically, the point I'm trying to make is that the number of samples is much less compared to the universe. And so, what that makes, what that sort of, so the issue where the place where it sort of shows up is that when you're learning any kind of model over this very large space, let's say you're learning a decision tree. Right? When you're learning a decision tree, you're explicitly taking sort of decisions on combinations of features. And if this feature combination is something that has not appeared in your training data, you won't be able to act on it on your test data at all. Right? And this is where sparsity sort of really becomes an issue. Okay? And it sort of really hurts the fact that we really want to generalize our model from the training data to the test data. Okay? So let's maybe that's enough of a motivation. So, okay. So let's kind of start with one specific way of doing dimension reduction. And this you guys have done. So I'm just going to get the answers from you again. So suppose we start with our data being represented as a matrix. Let's say that the matrix is n by d. And we call the matrix to be A. Right? And I want to define what is known as the singular value decomposition of the matrix. So what is the definition of a singular value decomposition of the matrix A? What is one definition that you might have seen? Pseudo inverse of A. Pseudo inverse of A is a specific matrix, right? And we can come to that. But the question I'm asking is that there's something called a singular value decomposition of A, which I think Sridhar has covered as far as I know. If you don't remember, that's fine. We'll go over this again. But anybody remembers this? Yes? No? Okay.
Every matrix can be divided into 15 matrices.
Okay.
The first is lower diameter and this last one is upper diameter and greater one is diameter.
Okay, let's go over this. Let's go over this slowly. So suppose we say that our matrix is of size n by d, right? There's a very nice theorem that says that every such matrix that's on reals can be written as a product of three matrices. Okay. So every matrix, every n by d matrix that is of rank R. Okay, what is the rank of a matrix? Number of linearly independent rows or columns, and the row rank of a matrix is equal to the column rank of a matrix. So we can just talk about the rank of the matrix. Okay. So every n by d matrix of rank R can be written as a product of three matrices. So what? The interesting thing is that these three matrices have very special properties, right? What are the special properties? Let's call this matrix as U, sigma, and V transpose. So the sigma is a diagonal matrix, sigma R, right? So U is going to be of size n by R, sigma is of size R by R, and V transpose is of size R by D, which means that V is of size D by R, okay? So sigma is a diagonal matrix and the entries are all non-zero. Right? In fact, I mean it's easy to see that you can sort of rearrange the columns of U and the entries of sigma and the rows of V transpose to make sure that the sigma values are actually decreasing. That sigma 1 is the biggest one, sigma 2 is the next biggest one among the sigma entries, sigma 3 is the third biggest one, and so on, and sigma r is the smallest one. Right? This is just a question of rearrangement. The interesting thing is that U has orthonormal columns. What does that mean? When I say that the matrix U has orthonormal columns, every column has two things. It means two things. The magnitude of the L2 norm of every column is 1. That's 1. And any two columns are orthogonal to each other, right? Which means that U transpose U is actually identity. Okay? That's an easy way of writing this. The matrix V is also orthonormal columns. Or rather, V transpose is orthonormal rows. Okay? So this is called the singular value decomposition of a matrix. Okay? So there are many ways of sort of writing this, right? And we'll sort of see we'll explore some properties of this. But is this clear? Okay. So do you guys remember how do you define eigenvalues, eigenvectors, for instance? Okay. And okay, let me ask this question. Does every real matrix have a eigenvalue decomposition? Yes? No? Yes, no? So we have two views. Huh? There might be complex eigenvalues. And how about you? You meant the same thing? Okay. Okay. So let's stick to real eigenvalues. So then you're saying that every matrix does not at least have real eigenvalues. That's a good point. Yes. But the singular value decomposition always exists for a matrix. And also the eigenvalue decomposition doesn't even make sense if the matrix is not square. Right? If the matrix is not square, then where are you going to get the eigenvectors? Right? It doesn't even make sense. So it at least has to be square. Here the matrix doesn't even need to be square. Right? So in some sense it's quite different. So one view of this is quite different from that of eigenvalue decomposition. However, there are very tight connections with eigenvalue decompositions, and we'll come to that.